You're standing in a laboratory, watching a physicist prepare what appears to be the simplest possible experiment. A single particle, a detector, a measurement. Nothing more complex than checking whether a light switch is on or off. The physicist presses a button, records a number, and announces the result. From the outside, this looks like the most straightforward interaction imaginable between a human being and the physical world. But if you ask that same physicist to explain what just happened, something unexpected occurs. They'll start talking about wave functions collapsing, about the role of observation, about the mysterious boundary between quantum and classical behaviour. And then, almost inevitably, the conversation drifts toward consciousness. Not because the physicist particularly wants to discuss consciousness, but because the mathematics of quantum mechanics seems to demand it. The equations that govern the particle's behaviour work perfectly, yet they contain a gap that pure physics cannot seem to fill. This is where a quiet discomfort begins to settle in. For nearly a century, consciousness has been appearing in discussions of quantum mechanics, like an uninvited guest who won't leave the party. Not because physicists are mystical thinkers, but because the theory itself seems to require something beyond matter and energy to make complete sense, and that question refuses to go away. The story begins in 1932 with a Hungarian mathematician named John von Neumann, who was trying to give quantum mechanics a solid mathematical foundation. Von Neumann was not someone given to wild speculation. He was methodical, precise, interested in building rigorous mathematical structures that could support the weight of experimental evidence. When he examined the quantum formalism, he discovered something troubling. According to the mathematics, quantum systems exist in what physicists call superposition. A particle can be in multiple states simultaneously until the moment it's measured. The equations describe this beautifully, predicting the probabilities of different outcomes with extraordinary accuracy. But they also reveal a fundamental problem. When exactly does the superposition end and a definite measurement result appear? Von Neumann traced the measurement process step by step. The quantum system interacts with a measuring device, but the measuring device is also made of quantum components, so it should also be in superposition. The device sends a signal to a recording apparatus, but that apparatus is also made of quantum parts. At what point in this chain does the fuzzy quantum world give way to the definite classical world we experience? Von Neumann concluded that the chain had to end somewhere with something that could not be described by quantum mechanics, something that was fundamentally different from the quantum systems being measured. He called this the final observer, and he suggested it might be human consciousness itself. Not because consciousness was magical, but because it seemed to be the one thing in the measurement chain that couldn't be decomposed into further quantum components. This was not the conclusion von Neumann wanted to reach. It was the conclusion the mathematics seemed to force upon him, and it opened a door that physicists have been trying to close ever since. The problem deepened in 1935 when Erwin Schrödinger, trying to illustrate the absurdity of applying quantum mechanics to everyday objects, described his famous thought experiment: a cat in a box connected to a quantum system that might or might not trigger a poison mechanism. According to the quantum formalism, until someone opens the box and observes the cat, it exists in a superposition of being both alive and dead. Schrödinger intended this as a reductio ad absurdum, a way of showing that quantum mechanics must be incomplete because it led to ridiculous conclusions. But instead of resolving the paradox, physicists found themselves forced to take it seriously. If quantum mechanics applies universally, then the cat really should be in superposition until observed. But observed by what? And how does the observation transform a quantum superposition into a definite classical outcome? The measurement problem, as it came to be known, created a conceptual crisis that continues today. The quantum equations are supremely successful at predicting experimental results, yet they seem to require an element that exists outside the physical systems they describe, something that can observe without being observed, measure without being measured, collapse wave functions without itself being in superposition. In 1961, the Nobel Prize-winning physicist Eugene Wigner pushed von Neumann's insight to its logical extreme. Wigner proposed a thought experiment that has become one of the most unsettling scenarios in quantum mechanics. Imagine that Wigner's friend is alone in a laboratory, performing a quantum measurement. From the friend's perspective, the measurement has a definite outcome. The wave function has collapsed. Reality has crystallized into a specific result. But from Wigner's perspective, standing outside the laboratory, the entire system, including his friend, should be described by quantum mechanics. The friend and the quantum system should be entangled, existing in a superposition of all possible measurement outcomes. According to the mathematics, Wigner's friend should be simultaneously in a state of having measured one result and having measured a completely different result. Which description is correct? Has the wave function collapsed for the friend but not for Wigner? When exactly did consciousness enter the picture? Wigner argued that consciousness must be the decisive factor, the element that transforms quantum possibilities into classical actualities. But this raised profound questions about the nature of consciousness itself and its role in physical reality. The Wigner's friend paradox reveals something deeply unsettling about quantum mechanics. It suggests that reality might not be objective in the way we normally assume. Instead, what counts as real might depend on who is observing and from what perspective. This is not a comfortable conclusion for physicists, who generally prefer their theories to describe a single, consistent reality that exists independent of observers. Yet the mathematics appears to demand this conclusion. Recent experiments have even tested versions of Wigner's friend scenario, confirming that quantum mechanics really does allow for incompatible descriptions of the same physical situation. The predictions of quantum theory hold up, but they force us to question fundamental assumptions about the nature of reality and observation. Throughout the 1960s and 1970s, as quantum mechanics matured and found applications in technology, the consciousness question persisted. Physicists developed various interpretations of quantum mechanics, each attempting to resolve the measurement problem in different ways. Some embraced the role of consciousness explicitly, others tried to eliminate it entirely, but none succeeded in making the question disappear. The many worlds interpretation proposed by Hugh Everett III suggested that all possible quantum outcomes actually occur, but in parallel universes that branch off from each other at every measurement. This eliminates the need for wave function collapse and seemingly removes consciousness from the picture, but it raises its own profound questions about the nature of reality and our experience of it. If all outcomes happen, why do we experience only one branch? What determines which branch contains our consciousness? Other interpretations attempted to solve the problem by modifying quantum mechanics itself. The pilot wave theory proposed that particles have definite positions guided by a quantum field. Spontaneous collapse theories suggested that wave functions collapse randomly without any external trigger. Each approach had its merits, but none achieved universal acceptance. The measurement problem remained, and with it, the nagging question of consciousness. As quantum mechanics found practical applications in lasers, transistors, and eventually quantum computers, the foundational questions became more pressing rather than less so. How can we build quantum technologies if we don't fully understand what quantum measurements actually accomplish? How can we control quantum systems if we're uncertain about the role of observation in determining their behavior? The development of quantum computing has added new dimensions to these questions. Quantum computers operate by maintaining systems in superposition and manipulating them through carefully controlled operations. But they must eventually produce classical outputs that can be read by classical computers and understood by human operators. This requires the same kind of quantum to classical transition that troubled von Neumann and Wigner. Computer scientists working on quantum algorithms found themselves grappling with measurement problems that physicists had been debating for decades. When exactly does a quantum computation become a classical result? What role does information play in the transition? And how do we understand the relationship between quantum information processing and classical information processing in systems that might themselves be conscious? These questions became more than academic when researchers began investigating whether biological systems might use quantum effects. In the 1990s, studies of photosynthesis revealed that plants might use quantum coherence to transfer energy with remarkable efficiency. Other research suggested that quantum effects might play a role in bird navigation, enzyme catalysis, and even the sense of smell. If quantum effects operate in biological systems, then the boundary between quantum and classical behavior might not be as clear as physicists had assumed. Living systems exist in warm, noisy environments that should destroy quantum coherence rapidly. Yet experiments suggested that some biological processes might maintain quantum effects for surprisingly long periods. This opened the possibility that consciousness itself might involve quantum processes. After all, consciousness emerges from the operation of the brain, which is a biological system. If other biological systems can maintain quantum coherence, perhaps the brain does too. And if consciousness involves quantum effects, then its role in quantum measurement might not be an external addition to physics, but an integral part of how quantum systems behave in complex environments. The most ambitious attempt to connect consciousness and quantum mechanics came from the unlikely collaboration between mathematician Roger Penrose and anesthesiologist Stuart Hameroff. In the 1990s, they proposed that consciousness arises from quantum processes in cellular structures called microtubules, found throughout the brain's neurons. According to their theory, called orchestrated objective reduction, consciousness occurs when quantum superpositions in microtubules reach a critical threshold and collapse according to fundamental features of space-time geometry. This process, they argued, could explain both the hard problem of consciousness and the measurement problem in quantum mechanics. Consciousness would be the mechanism by which quantum possibilities become classical realities. The Penrose-Hameroff theory was controversial from the start. Many scientists argued that the brain is too warm and noisy to maintain the quantum coherence required for their model. Others questioned whether quantum effects at the molecular level could influence neural computation in meaningful ways. The theory required exotic physics that had never been observed in biological systems. But the theory also made testable predictions. It suggested that anesthetics work by disrupting quantum processes in microtubules, providing a potential explanation for how consciousness can be selectively eliminated while leaving other brain functions intact. It predicted specific timescales for conscious events based on the dynamics of quantum collapse, and it offered a framework for understanding how quantum effects might scale up from molecular to psychological levels. Recent research has provided some support for quantum effects in microtubules, though not necessarily in the way Penrose and Hameroff originally envisioned. Studies have found evidence for quantum coherence in the protein structures that make up microtubules. Other research has suggested that anesthetics might indeed target the quantum properties of these cellular components. More broadly, the field of quantum biology has matured significantly, demonstrating that quantum effects can persist in biological environments under specific conditions. This has made the possibility of quantum consciousness seem less outlandish than it did when Penrose and Hameroff first proposed their theory. Yet even if consciousness does involve quantum processes, this would not automatically resolve the measurement problem. We would still need to understand how conscious observation differs from other types of physical interaction. We would still need to explain why consciousness seems to play a special role in determining the outcomes of quantum measurements. The persistence of these questions has led some physicists to embrace interpretations of quantum mechanics that explicitly incorporate consciousness. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no time parameter and no explicit mechanism for wave function collapse. Some physicists have suggested that consciousness provides the missing element, serving as the internal clock that gives meaning to the evolution of the quantum state. Other physicists have moved in the opposite direction, arguing that consciousness plays no fundamental role in quantum mechanics, and that the appearance of such a role results from conceptual confusion. They point out that quantum measurements can be performed by completely automated systems with no conscious observers present. The quantum Zeno effect demonstrates that frequent measurements can freeze the evolution of quantum systems, whether those measurements involve consciousness or not. This is where intuition usually begins to strain. On one hand, quantum mechanics works perfectly well as a practical theory for making predictions and building technologies. Quantum computers operate successfully. Quantum sensors achieve unprecedented precision, and quantum communication systems provide unbreakable security. None of these applications seem to require consciousness in any fundamental way. On the other hand, the foundational questions about measurement and observation remain as mysterious as ever. We can use quantum mechanics without understanding what quantum measurements actually accomplish. We can build quantum technologies without knowing why the quantum world gives way to the classical world we experience. We can manipulate quantum states without comprehending the nature of the boundary between quantum and classical behavior. And consciousness keeps appearing in these discussions not because physicists are particularly interested in consciousness, but because the structure of quantum mechanics seems to demand something like it. The theory requires a distinction between the system being measured and the apparatus performing the measurement. It requires a boundary between the quantum realm of superposition and the classical realm of definite outcomes. It requires something that can observe without being fully described by the quantum formalism itself. The mystery deepens when you realize that every attempt to eliminate consciousness from quantum mechanics has only made its appearance more pronounced. Consider the decades-long effort to develop what physicists call objective interpretations of quantum theory. These are mathematical frameworks designed specifically to remove any reference to observers, measurements, or conscious agents. Yet each of these interpretations has encountered the same stubborn obstacle. Take spontaneous collapse theories, which propose that quantum wave functions simply collapse randomly at certain intervals, without any external trigger. The mathematics can be made to work, but only by introducing arbitrary parameters that determine when and how these collapses occur. The theory requires us to believe that nature contains a fundamental randomness that operates according to rules we must simply accept without deeper explanation. And when physicists try to determine what these rules should be, they find themselves making choices that seem to privilege the scale of conscious experience. The collapse rate must be slow enough that microscopic quantum effects remain coherent, yet fast enough that macroscopic objects like measurement devices and brains never exist in noticeable superposition. This is not a coincidence that emerges from the theory. It is a requirement that must be built into the theory to match our experience of a classical world. The mathematics works, but it feels suspiciously tailored to accommodate the very thing it was designed to eliminate. Pilot wave theory represents another ambitious attempt to restore objective reality to quantum mechanics. In this interpretation, particles have definite positions and velocities at all times, guided by a quantum wave that exists independently of observation. The wave is real, the particles are real, and measurements simply reveal pre-existing properties rather than creating them. This eliminates the measurement problem by denying that there was ever a problem to solve. Yet pilot wave theory introduces its own puzzles that circle back toward consciousness. The theory requires a fundamental distinction between the configuration of particles that represents the actual state of the system and all the other possible configurations that exist only as mathematical possibilities in the wave function. But what determines which configuration is actual? The theory provides no physical mechanism for this selection. The actual configuration must simply be given as an additional postulate, and that postulate inevitably connects to what observers actually observe. Even more puzzling, pilot wave theory leads to a form of environmental determinism that seems to eliminate free will more completely than any other interpretation of quantum mechanics. If particle positions are always definite and their motion is completely determined by the wave function, then human decision-making becomes just another mechanical process with no room for genuine choice. This creates a philosophical tension that many find more troubling than the original measurement problem. The many worlds interpretation takes a different approach entirely, embracing the full implications of the quantum formalism without modification. Every quantum measurement causes the universe to split into parallel branches corresponding to each possible outcome. There is no wave function collapse because every possibility actually occurs in some branch of reality. The appearance of collapse results from our limited perspective as conscious beings who can experience only one branch at a time. This interpretation eliminates consciousness from the fundamental physics while making it absolutely central to our understanding of quantum mechanics. We need consciousness to explain why we observe definite outcomes despite the fact that all outcomes actually occur. We need consciousness to explain the appearance of probability in a deterministic theory where everything that can happen does happen. We need consciousness to explain why quantum mechanics seems to describe our experience when that experience represents only an infinitesimal fraction of physical reality. The many worlds interpretation forces us to confront questions about consciousness that go far beyond quantum mechanics. If every decision you could make creates a new branch of reality containing a version of you that made that decision. What makes your consciousness special? Why do you experience this particular branch rather than one of the countless others? What determines the continuity of conscious experience across quantum events that are constantly creating new branches? These questions have led some physicists to propose that consciousness itself might split along with the physical world, creating multiple streams of awareness that diverge at each quantum measurement. But this raises even deeper puzzles about the nature of personal identity and the unity of conscious experience. Are there countless versions of you reading these words right now, each slightly different due to quantum events that occurred during the processing of this information in your brain? The persistent appearance of consciousness in these discussions reflects something profound about the structure of quantum mechanics itself. The theory is formulated in terms of information rather than classical physical quantities. Quantum states are described by mathematical objects that encode what can be known about a system rather than what the system actually is in any classical sense. Measurements are described as processes that extract information from these states rather than simply revealing pre-existing properties. This informational character of quantum mechanics creates a natural connection to consciousness, which is itself fundamentally concerned with information processing. When we observe a quantum system, we gain information about it. But information is not a purely objective physical quantity like mass or charge. Information exists only in relation to something that can process, store, and interpret it. This raises profound questions about the relationship between physical processes and informational content. Consider the quantum measurement process from an informational perspective. Before measurement, a quantum system exists in a superposition that contains multiple possibilities. The measurement extracts specific information from this superposition, converting quantum information into classical information. But what determines which information gets extracted? And how does the extraction process relate to the conscious experience of learning the measurement result? These questions become particularly acute when we consider quantum information theory, which has revealed deep connections between information, computation, and consciousness. Quantum computers can process certain types of information exponentially faster than classical computers, but they require careful isolation from environmental interference. The moment quantum information interacts with the environment in an uncontrolled way, it becomes classical information through a process called decoherence. Decoherence was initially seen as a solution to the measurement problem. It explains how quantum superpositions become effectively classical through interaction with complex environments without requiring any special role for consciousness or measurement devices. The environment acts as a continuous monitoring system that destroys quantum coherence and creates the appearance of classical behavior. But decoherence creates its own conceptual puzzles that bring consciousness back into focus. The theory explains why we don't observe macroscopic superpositions, but it doesn't explain why we observe anything at all. Decoherence produces what physicists call an improper mixture, a quantum state that behaves classically for most practical purposes, but still technically exists in superposition. The transition from an improper mixture to the definite classical states we actually experience remains unexplained. This is where the quantum information perspective reveals something unsettling about the relationship between consciousness and physical reality. Information processing requires not just the physical storage and manipulation of data, but also something that can interpret that data as meaningful. A quantum computer can process information, but it cannot understand what that information represents. Understanding requires consciousness. The connection becomes even more intriguing when we consider recent developments in quantum biology. Living systems have evolved sophisticated mechanisms for processing information at the molecular level, and some of these mechanisms appear to exploit quantum effects. Photosynthesis uses quantum coherence to achieve remarkable efficiency in energy transfer. Bird navigation might depend on quantum entanglement in specialized proteins. Even the sense of smell might involve quantum tunneling effects. These discoveries suggest that the boundary between quantum and classical behavior is not as sharp as physicists once believed. Living systems exist at the interface between these two regimes, using quantum effects, when they provide advantages while maintaining classical functionality for information processing and decision-making. Consciousness emerges from this complex hybrid system that operates according to both quantum and classical principles. The brain itself represents the most sophisticated information processing system we know of, integrating signals from billions of neurons to create unified conscious experiences. Recent research has found evidence for quantum effects in the cellular structures that make up neurons, including the microtubules that Penrose and Hameroff identified as potential sites of quantum consciousness. While the original orchestrated objective reduction theory remains controversial, the basic finding that biological systems can maintain quantum coherence has become increasingly well established. Even more intriguingly, anesthetic drugs that eliminate consciousness appear to target the same cellular structures where quantum effects have been detected. The correlation between anesthetic potency and the disruption of quantum processes in microtubules provides a potential bridge between quantum mechanics and consciousness that can be tested experimentally. If consciousness depends on quantum coherence in neural structures, then drugs that disrupt this coherence should eliminate consciousness, which is exactly what we observe. These biological connections have inspired new theoretical frameworks that attempt to understand consciousness as an emergent property of quantum information processing in neural networks. According to these theories, consciousness arises when quantum information becomes integrated across multiple brain regions in a way that creates unified experiences from distributed neural activity. The integration process requires maintaining quantum coherence over relatively long distances and timescales, which explains why consciousness is such a rare and delicate phenomenon. But even these sophisticated biological theories face the same fundamental conceptual challenges that have plagued quantum mechanics since its inception. They can describe the mechanisms by which consciousness might emerge from quantum processes, but they cannot explain why these processes should give rise to subjective experience rather than simply more complex forms of information processing. The hard problem of consciousness remains as mysterious as ever, even when approached through quantum mechanics. This persistence of mystery reflects something deeper about the relationship between consciousness and quantum mechanics. Both involve the transformation of possibilities into actualities, the conversion of potential information into definite states. In quantum mechanics, measurement transforms superpositions into classical outcomes. In consciousness, neural processing transforms sensory data into unified experiences. These processes might be more closely related than we typically assume. The quantum measurement problem and the hard problem of consciousness share a similar logical structure. Both involve a gap between objective physical processes and subjective experiences or outcomes. Both require something that can observe without being fully reducible to the systems being observed. Both suggest that our current scientific frameworks might be incomplete in fundamental ways. Some physicists have begun to explore whether these problems might have a common solution. Perhaps consciousness and quantum measurement are two aspects of a more fundamental process by which reality crystallizes from possibilities. Perhaps the observer in quantum mechanics and the subject in consciousness studies refer to the same basic phenomenon viewed from different perspectives. This possibility has led to new experimental approaches that attempt to test connections between consciousness and quantum mechanics directly. Researchers are investigating whether conscious intention can influence quantum measurements in ways that go beyond the standard predictions of quantum mechanics. Others are exploring whether quantum entanglement can be detected in neural processes during conscious experiences. These experiments remain controversial, and their results are often disputed, but they represent a serious attempt to move beyond philosophical speculation toward empirical investigation. If consciousness does play a fundamental role in quantum mechanics, this should be detectable through carefully designed experiments. If it doesn't, these experiments should help clarify why consciousness keeps appearing in discussions of quantum theory, despite having no actual physical relevance. The experimental challenges are formidable because they require isolating potential quantum effects in consciousness from the many other factors that influence both conscious experience and quantum measurements. The brain is an incredibly complex system that processes information through both quantum and classical mechanisms. Separating these different contributions requires experimental techniques that can probe quantum coherence in living neural tissue without disrupting the delicate processes that support consciousness. Recent advances in quantum sensing and brain imaging are beginning to make such experiments possible. Researchers have developed techniques for detecting quantum entanglement in biological systems and for monitoring quantum coherence in neural processes. While these methods are still in their early stages, they offer the possibility of directly testing whether consciousness involves quantum effects in the ways that various theories predict. But even if these experiments succeed in detecting quantum processes in consciousness, this would not automatically resolve the measurement problem in quantum mechanics. We would still need to understand how conscious observation differs from other types of physical interaction, and why consciousness seems to play a special role in determining the outcomes of quantum measurements. The connection between quantum mechanics and consciousness might be real without being fundamental. This is where intuition usually begins to strain. We are accustomed to thinking of consciousness as something that emerges from brain activity, which in turn emerges from molecular interactions governed by the laws of physics. In this hierarchical picture, consciousness is a high-level phenomenon that depends on lower-level physical processes, but does not influence them in any fundamental way. But quantum mechanics suggests a different picture in which observation and measurement play constitutive roles in determining physical reality. If consciousness is the mechanism by which quantum possibilities become classical actualities, then it is not simply an emergent property of complex physical systems, but a fundamental feature of how those systems behave. This would represent a radical revision of our understanding of the relationship between mind and matter. The implications extend far beyond quantum mechanics into questions about free will, personal identity, and the nature of reality itself. If consciousness plays a fundamental role in physical processes, then the boundary between subjective experience and objective reality becomes blurred in ways that challenge basic assumptions about the nature of scientific knowledge. How can we study consciousness objectively if consciousness is involved in the very process of observation that makes objective study possible? These philosophical implications help explain why consciousness keeps appearing in discussions of quantum mechanics, despite the best efforts of physicists to develop purely objective interpretations. The structure of quantum theory seems to require something that can observe without being fully described by the theory itself. Whether we call this something consciousness, measurement, information processing, or environmental interaction, it represents a boundary condition that the theory cannot fully explain. This boundary condition reflects a deeper tension between the mathematical formalism of quantum mechanics and our conceptual understanding of physical reality. The mathematics works perfectly for making predictions and building technologies, but it describes reality in terms that seem to require conscious interpretation to become meaningful. Wave functions, probability amplitudes, and quantum states are mathematical abstractions that represent potential information rather than definite physical properties. The transformation of these mathematical abstractions into the concrete physical properties we observe and measure remains one of the deepest mysteries in quantum mechanics. Some physicists argue that this transformation is purely mathematical, a consequence of the way quantum information interacts with complex environments. Others suggest that it requires something beyond mathematics, a physical process that converts possibilities into actualities. And consciousness keeps appearing in these discussions not because physicists are particularly interested in consciousness, but because consciousness represents the most familiar example of something that can process information and make determinations about reality. We know from direct experience that consciousness can observe, measure, and interpret physical systems. Whether consciousness plays any special role in quantum mechanics remains an open question, but it provides a conceptual framework for thinking about the kinds of processes that quantum mechanics seems to require. The persistence of this framework suggests something profound about the limits of purely objective approaches to understanding reality. Perhaps consciousness appears in quantum mechanics because both involve aspects of reality that cannot be fully captured from a purely third-person, objective perspective. Perhaps the measurement problem and the hard problem of consciousness are symptoms of the same underlying limitation in our scientific worldview. And perhaps the most unsettling part is not that we don't have definitive answers to these questions, but that the questions themselves keep evolving in ways that reveal new depths of mystery. Each attempt to resolve the connection between consciousness and quantum mechanics opens new puzzles that seem to require even more fundamental revisions to our understanding of reality. The experimental challenges become even more perplexing when you examine what happens at the intersection of quantum information theory and biological systems. Recent advances in quantum sensing have made it possible to detect quantum coherence in living tissue, and the results have been quietly revolutionary. Researchers can now observe quantum entanglement persisting in protein structures at body temperature, quantum tunneling effects in enzyme catalysis, and coherent energy transfer in photosynthetic complexes. These findings demolish the old assumption that warm, wet biological environments automatically destroy quantum effects. But they also create a new puzzle. If quantum coherence can survive in biological systems, and if consciousness emerges from biological processes in the brain, then the relationship between quantum mechanics and consciousness becomes an empirical question rather than a philosophical one. we can actually investigate whether conscious processes involve quantum effects in ways that might be relevant to quantum measurement theory. The most systematic attempt to bridge this gap has come from researchers studying anesthetic action. For over a century, doctors have known that certain gases can reversibly eliminate consciousness while leaving other brain functions largely intact. The Meyer-Overton correlation shows that anesthetic potency correlates precisely with how well these molecules dissolve in lipid membranes. But recent research suggests this correlation might reflect something deeper about the physical basis of consciousness. When anesthetic molecules interact with neural proteins, they appear to disrupt quantum coherence in the cellular structures that support conscious processing. The same drugs that eliminate consciousness also eliminate the quantum effects that some theories predict should be necessary for conscious experience. This correlation doesn't prove that consciousness depends on quantum mechanics, but it provides a testable connection between quantum processes and the presence or absence of conscious awareness. The implications extend beyond anesthesia into broader questions about information integration in the brain. Consciousness seems to require the binding of distributed information processing into unified experiences. When you see a red apple, neural processes in different brain regions encode information about colour, shape, texture, and meaning. Yet your conscious experience integrates all this information into a single, coherent perception. This binding process might require quantum entanglement between different neural regions, allowing information to be correlated across the brain in ways that classical physics cannot easily explain. The quantum coherence observed in biological systems might serve precisely this function, creating the informational unity that characterizes conscious experience. If this is correct, then consciousness represents a macroscopic quantum phenomenon that emerges from the collective behavior of many microscopic quantum processes. But even this sophisticated picture leaves fundamental questions unanswered. Why should quantum information integration give rise to subjective experience rather than simply more complex forms of information processing? What distinguishes the quantum processes associated with consciousness from the quantum processes that occur throughout the physical world? And how does the subjective experience of consciousness relate to the objective processes of quantum measurement? These questions reveal something profound about the limits of purely physical approaches to understanding consciousness. Every attempt to explain consciousness in terms of neural activity, whether classical or quantum, faces the same explanatory gap. We can describe the mechanisms by which information is processed and integrated, but we cannot explain why these mechanisms should be accompanied by subjective experience. The hard problem of consciousness persists regardless of whether we invoke classical or quantum physics. Yet quantum mechanics adds a new dimension to this ancient puzzle. If consciousness involves quantum processes, then conscious observers are not simply passive recipients of information about quantum systems. They are active participants in quantum processes themselves. The boundary between the measuring apparatus and the system being measured becomes blurred when the measuring apparatus includes conscious agents whose own functioning involves quantum effects. This blurring of boundaries creates conceptual problems that go beyond the traditional measurement problem. In the standard formulation of quantum mechanics, there is a clear distinction between the quantum system being measured and the classical measuring apparatus. But if consciousness involves quantum processes, then conscious observers exist simultaneously in both the quantum and classical realms. They are quantum systems that can observe other quantum systems. classical systems that can process quantum information. The mathematical formalism of quantum mechanics was not designed to handle such hybrid systems. When quantum mechanics was developed in the early 20th century, consciousness was assumed to exist outside the physical systems described by the theory. Conscious observers were treated as external agents who could perform measurements and record results without themselves being subject to quantum mechanical description. But this assumption becomes untenable if consciousness involves quantum processes. A conscious observer, who is simultaneously a quantum system and a classical measuring apparatus, cannot be described adequately by either the quantum mechanical formalism or classical physics alone. Such systems require new mathematical frameworks that can handle the complex interplay between quantum and classical processes in biological systems. Recent developments in quantum biology have begun to provide such frameworks. Researchers have developed models of quantum information processing in biological systems that account for the partial decoherence that occurs in warm, noisy environments. These models show how quantum effects can persist and influence biological function even when they are not perfectly isolated from environmental disturbances. The key insight is that biological systems have evolved mechanisms for protecting quantum coherence in specific contexts while allowing decoherence in others. Photosynthetic complexes maintain quantum coherence for energy transfer while allowing decoherence for thermal regulation. Neural systems might similarly maintain quantum coherence for information integration while allowing decoherence for signal transmission. This selective preservation of quantum coherence suggests that consciousness might involve a delicate balance between quantum and classical processes. Conscious experience might emerge from quantum information integration that occurs on timescales and length scales where coherence can be maintained, while motor control and other brain functions might rely on classical processes that are more robust to environmental disturbances. If this picture is correct, then consciousness represents a remarkable evolutionary achievement. Biological systems have learned to exploit quantum mechanics for information processing while maintaining the classical reliability necessary for survival in macroscopic environments. Consciousness emerges at the interface between these quantum and classical processes, requiring both for its full realization. But this evolutionary perspective raises new questions about the role of consciousness in quantum measurement. If consciousness evolved as a mechanism for processing quantum information, then its appearance in discussions of quantum mechanics might reflect something deeper than conceptual confusion. Conscious observation might be qualitatively different from other forms of physical interaction, precisely because consciousness has evolved to process quantum information in ways that other classical systems cannot. This possibility has led some researchers to investigate whether conscious intention can influence quantum measurements in ways that go beyond the standard predictions of quantum mechanics. These experiments remain highly controversial, and their results are often disputed, but they represent a serious attempt to test whether consciousness plays any special role in quantum processes beyond what can be explained by conventional physics. The experimental challenges are formidable because they require detecting extremely subtle effects in the presence of much larger sources of noise and systematic error. Any influence of consciousness on quantum measurements would have to be distinguished from the many other factors that can affect quantum systems, including electromagnetic fields, temperature fluctuations, and mechanical vibrations. Even more challenging, such experiments must account for the psychological factors that can influence both conscious intention and the interpretation of experimental results. researchers must design protocols that eliminate confirmation bias, placebo effects, and other forms of experimenter influence, while still allowing for the possibility that consciousness might have genuine physical effects. Despite these challenges, some experiments have reported anomalous results that might indicate consciousness-related effects in quantum systems. These results remain controversial and have not been independently replicated to the satisfaction of the broader scientific community. But they suggest that the relationship between consciousness and quantum mechanics might be more complex than either pure materialists or pure idealists typically assume. The controversy surrounding such experiments reflects deeper disagreements about the nature of consciousness and its relationship to physical processes. Some researchers argue that consciousness is purely emergent from classical neural activity and cannot have any direct influence on quantum systems. Others suggest that consciousness might involve quantum processes that could, in principle, influence other quantum systems through entanglement or other non-local effects. These disagreements cannot be resolved through philosophical arguments alone. They require empirical investigation using the most sophisticated experimental techniques available. But the experiments themselves are pushing the boundaries of what current technology can reliably measure, and the interpretation of results requires careful consideration of both quantum mechanical and psychological factors. This is where the question becomes not just scientific but also deeply personal. If consciousness does involve quantum processes, and if these processes can influence quantum measurements, then every conscious observer is both a subject experiencing reality and an agent participating in the creation of that reality. The boundary between observer and observed, between subject and object, becomes fundamentally ambiguous. Such ambiguity challenges basic assumptions about the nature of scientific knowledge and objective reality. Science has traditionally been based on the assumption that there is a clear distinction between the knower and the known, between the observer and the observed system. But quantum mechanics, especially when combined with theories of quantum consciousness, suggests that this distinction might be less fundamental than we typically assume. The implications extend beyond physics into questions about free will, personal identity, and moral responsibility. If consciousness plays a role in determining the outcomes of quantum measurements, and if quantum processes influence neural activity, then conscious choice might have genuine causal efficacy in the physical world. This would provide a potential mechanism for free will that is consistent with physical law, while allowing for genuine agency. But such possibilities also raise troubling questions about the nature of personal identity and moral responsibility. If consciousness involves quantum processes that are inherently probabilistic, then the choices we make might be influenced by fundamental randomness in ways that we cannot control or predict. The relationship between quantum indeterminacy and free will remains deeply unclear. These philosophical implications help explain why consciousness keeps appearing in discussions of quantum mechanics, despite the best efforts of physicists to develop purely objective interpretations. The structure of quantum mechanics seems to require something that can observe, measure, and collapse wave functions. Whether we identify this something with consciousness, measurement apparatus, or environmental decoherence, it represents a boundary condition that the theory cannot fully explain from within its own formalism. This boundary condition reflects a deeper tension between the mathematical precision of quantum mechanics and the conceptual clarity that we expect from scientific theories. Quantum mechanics provides extraordinarily accurate predictions for the behavior of microscopic systems, but it does so using mathematical abstractions that seem to require conscious interpretation to become meaningful. Wave functions, probability amplitudes, and quantum superpositions are not directly observable quantities. They are mathematical constructs that encode information about what can be measured under different experimental conditions. The transformation of these abstract mathematical objects into the concrete measurement results that we observe and record remains one of the deepest mysteries in quantum mechanics. Some physicists argue that this mystery is purely conceptual, reflecting our incomplete understanding of how mathematical formalism relates to physical reality. They suggest that future developments in quantum mechanics will eliminate the need for conscious observers or measurement apparatus by providing a complete description of all physical processes in purely objective terms. Other physicists argue that the mystery is more fundamental, reflecting inherent limitations in any purely objective approach to understanding reality. They suggest that consciousness appears in quantum mechanics because both consciousness and quantum measurement involve aspects of reality that cannot be fully captured from a purely third-person perspective. The debate between these perspectives has continued for nearly a century without reaching resolution. Each new interpretation of quantum mechanics promises to eliminate the need for conscious observers, yet consciousness continues to appear in subtle ways that resist elimination. The measurement problem persists despite decades of sophisticated theoretical development and experimental investigation. This persistence suggests that the relationship between consciousness and quantum mechanics might reflect something deeper about the nature of scientific knowledge itself. Perhaps consciousness appears in quantum mechanics not because consciousness explains quantum mechanics, but because both involve fundamental aspects of reality that our current scientific frameworks cannot adequately describe. The recognition of such limitations need not lead to mysticism or anti-scientific thinking. Instead, it might point toward new forms of scientific understanding that can accommodate the full richness of conscious experience while maintaining the precision and predictive power that makes science so valuable. Such understanding would require conceptual frameworks that can handle the complex interplay between subjective experience and objective processes. Recent developments in the foundations of quantum mechanics have begun to explore such frameworks. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire universe, including all observers and measuring apparatus. But this equation contains no time parameter and no explicit mechanism for the emergence of classical space-time and conscious observers from quantum processes. Some physicists have suggested that consciousness provides the missing element that gives meaning to the Wheeler-DeWitt equation. Conscious observers might serve as the internal clocks that define temporal evolution in a universe that is fundamentally timeless at the quantum level. But this suggestion raises as many questions as it answers about the nature of consciousness and its relationship to physical processes. Other approaches attempt to eliminate consciousness from fundamental physics, while acknowledging its importance for understanding how quantum mechanics relates to human experience. These approaches treat consciousness as an emergent property of complex information processing systems that can observe and interpret quantum processes without playing any fundamental role in determining their outcomes. But even these deflationary approaches must account for the special relationship between consciousness and quantum measurement. Conscious observers seem to have privileged access to measurement results in ways that other physical systems do not. When a quantum measurement is performed, conscious observers can know the result directly through their subjective experience, while other systems can only carry information about the result in their physical states. This epistemic asymmetry between conscious and non-conscious systems creates puzzles that persist even when consciousness is treated as purely emergent. If consciousness provides no special insight into the nature of quantum processes, why does it seem to be necessary for interpreting quantum measurements? If conscious observation is just another form of physical interaction, why does it seem to play such a central role in our understanding of quantum mechanics? The answers to these questions might lie in the unique informational properties of conscious systems. Consciousness might be distinguished not by its physical substrate, but by its capacity for certain kinds of information integration and interpretation. Conscious systems can represent information about quantum processes in ways that allow them to make predictions, form beliefs, and guide actions based on quantum mechanical knowledge. This informational perspective suggests that consciousness appears in quantum mechanics because conscious systems are uniquely capable of processing and interpreting quantum information. They can bridge the gap between the mathematical abstractions of quantum theory and the concrete experiences that give those abstractions meaning. Without conscious interpretation, quantum mechanics would remain a purely mathematical formalism with no connection to observable phenomena. But this perspective also raises new questions about the nature of information and its relationship to physical processes. If consciousness is fundamentally about information processing, and if quantum mechanics is fundamentally about information, then the connection between consciousness and quantum mechanics might be more intimate than either perspective typically assumes. Both might be aspects of a more fundamental informational structure that underlies all physical processes. Such possibilities remain highly speculative, but they illustrate how the question of consciousness in quantum mechanics continues to evolve in unexpected directions. Each attempt to resolve the connection between consciousness and quantum mechanics opens new avenues of investigation that reveal previously unrecognized depths of complexity. The question refuses to be definitively answered, not because it lacks content, but because it continues to reveal new aspects of reality that challenge our existing conceptual frameworks. And perhaps the most unsettling part is not that we don't have definitive answers to these questions, but that the questions themselves keep evolving in ways that reveal how much we still don't understand about the relationship between mind and matter, between subjective experience and objective processes, between the quantum realm of possibilities and the classical world of definite outcomes. Each new insight seems to deepen the mystery rather than resolve it, suggesting that consciousness and quantum mechanics might be pointing toward aspects of reality that lie beyond our current scientific paradigms entirely. The unsettling realization emerges gradually. You begin studying quantum mechanics, expecting to encounter strange behavior in atoms and particles, phenomena safely confined to the microscopic realm where intuition already admits defeat. But then you discover something unexpected lurking in the mathematics. Every attempt to describe what happens during a quantum measurement eventually encounters the same conceptual gap. The equations work perfectly for predicting probabilities, but they cannot explain why any particular outcome actually occurs. And in that gap, consciousness keeps reappearing like a persistent echo. Not because physicists want it there. Most would prefer a purely objective theory that requires no reference to observers, minds, or subjective experience. Yet the formal structure of quantum mechanics seems to resist such purification. Every interpretation designed to eliminate consciousness from the theory has encountered the same stubborn obstacle. Something must distinguish between the quantum realm of superpositions and the classical realm of definite outcomes. Something must explain why measurements yield specific results rather than remaining forever suspended in probabilistic limbo. And that question refuses to go away. The persistence of this connection reflects a deeper puzzle about the nature of physical reality itself. Classical physics operated under the comfortable assumption that the world exists in definite states, independent of observation. Objects have precise positions and velocities whether anyone measures them or not, but quantum mechanics undermines this assumption at its foundation. According to the mathematical formalism, quantum systems exist in superpositions of multiple possibilities until the moment of measurement transforms these possibilities into actualities. This transformation process lies at the heart of why consciousness keeps appearing in quantum theory. The mathematics describes superpositions with extraordinary precision, yet it provides no mechanism for explaining how or why these superpositions collapse into definite measurement outcomes. Something beyond the quantum formalism itself seems required to bridge this gap between mathematical possibility and physical actuality. The historical development of this puzzle reveals how deeply it is embedded in the structure of quantum theory. When Werner Heisenberg first formulated matrix mechanics in 1925, he explicitly avoided questions about what quantum systems are actually doing between measurements. His approach focused entirely on the mathematical relationships between observable quantities, leaving the underlying reality deliberately undefined. This pragmatic stance worked brilliantly for making predictions, but it left fundamental questions about the nature of quantum processes unresolved. Erwin Schrödinger's wave equation, developed shortly afterward, seemed to provide a more complete picture by describing the continuous evolution of quantum systems over time. But Schrödinger himself recognized that his equation led to paradoxical conclusions when applied to macroscopic objects. His famous thought experiment about a cat that exists in a superposition of being simultaneously alive and dead was designed to highlight the absurdity of applying quantum mechanics to everyday experiences. Yet instead of resolving the paradox, subsequent developments in quantum theory have only deepened the mystery. The mathematical formalism has been refined and extended to handle increasingly complex systems. But the fundamental question about the transition from quantum possibilities to classical actualities remains as puzzling as ever. Every attempt to solve this measurement problem has encountered the same conceptual obstacle: the need to identify something that can collapse wave functions without itself being subject to quantum mechanical description. This is where consciousness enters the discussion not as a solution, but as the most familiar example of something that seems to operate according to different principles than the quantum systems it observes. When a conscious observer performs a quantum measurement, they directly experience a definite outcome. This subjective experience of definiteness appears to be qualitatively different from the mathematical description of superposition states that quantum theory attributes to unmeasured systems. The distinction becomes particularly sharp when you consider the informational content of quantum measurements. Before measurement, a quantum system contains what physicists call quantum information, encoded in the complex mathematical structure of its wave function. This information includes all possible measurement outcomes, along with their associated probabilities, but it does not specify which outcome will actually occur. After measurement, this quantum information has been converted into classical information about a specific outcome, but information is not a purely objective, physical quantity like energy or momentum. Information exists only in relation to something that can process, interpret, and act upon it. A measuring device can record the outcome of a quantum measurement, but it cannot understand what that outcome means or how it relates to other measurements. Understanding requires something more than mechanical information processing. This requirement for interpretation creates a natural connection between quantum measurement and consciousness, which is fundamentally concerned with the meaningful interpretation of information. Conscious observers can not only record measurement results but also understand their significance, form beliefs about quantum systems based on measurement data, and use this understanding to make predictions about future measurements. The connection becomes even more intriguing when you examine the temporal structure of quantum measurements. According to the standard interpretation of quantum mechanics, the outcome of a measurement is not determined until the measurement actually occurs. This suggests that consciousness might play a role not just in interpreting measurement results, but in actualizing them from the realm of quantum possibilities. Some interpretations of quantum mechanics have embraced this possibility explicitly. The consciousness-based interpretations proposed by physicists like Eugene Wigner and later developed by Henry Stapp argue that conscious observation is the physical mechanism responsible for wave function collapse. According to these views, quantum systems remain in superposition until observed by a conscious agent, at which point the act of conscious observation causes the wave function to collapse into a definite state. These interpretations remain controversial, partly because they seem to violate the physicalist assumption that consciousness emerges from physical processes rather than influencing them. If consciousness can cause wave function collapse, then it possesses a form of causal efficacy that goes beyond what current neuroscience can explain. This creates a tension between quantum mechanics and our understanding of the brain as a classical information processing system. Yet attempts to eliminate consciousness from quantum mechanics have encountered their own conceptual difficulties. The decoherence program, developed in the 1970s and 1980s, attempted to explain the appearance of classical behavior through the interaction of quantum systems with their environments. According to this approach, quantum superpositions are constantly being disrupted by environmental interactions, creating the appearance of classical definiteness without requiring any special role for conscious observers. Decoherence theory has been remarkably successful in explaining many aspects of the quantum to classical transition, but it cannot fully eliminate the measurement problem. Environmental decoherence can explain why superpositions become practically unobservable, but it cannot explain why measurement outcomes become definite rather than remaining in what physicists call improper mixtures. Something still seems required to convert these mixtures into the definite classical states that conscious observers actually experience. The persistence of this explanatory gap has led to increasingly sophisticated attempts to understand the relationship between quantum mechanics and consciousness. Rather than treating consciousness as either the cause of wave function collapse or as irrelevant to quantum processes, recent approaches have begun exploring whether consciousness and quantum measurement might be two aspects of a more fundamental informational process. This informational perspective treats both consciousness and quantum mechanics as involving the processing and integration of information, but at different levels of organization. Quantum mechanics describes how information is encoded and transformed at the microscopic level, while consciousness involves the integration of information into unified experiences at the macroscopic level of neural networks. The connection between these levels becomes particularly interesting when you consider recent discoveries about quantum effects in biological systems. For decades, physicists assumed that the warm, noisy environments inside living cells would destroy quantum coherence too quickly for quantum effects to play any significant biological role. But experiments in quantum biology have revealed that some biological processes do indeed exploit quantum coherence for enhanced efficiency. Photosynthetic complexes maintain quantum coherence for surprisingly long periods, allowing energy to explore multiple pathways simultaneously before settling on the most efficient route to the reaction center. Some theories of bird navigation involve quantum entanglement in specialized proteins that might allow birds to literally see magnetic fields. Even the sense of smell might involve quantum tunneling effects that allow molecules with identical chemical structures but different vibrational frequencies to be distinguished by their quantum properties. These discoveries have made the possibility of quantum effects in consciousness seem less implausible than it appeared when quantum biology was purely speculative. If other biological systems can maintain and exploit quantum coherence, perhaps the brain does too. And if consciousness involves quantum processes, then its relationship to quantum measurement might be more than just conceptual analogy. The most detailed attempt to develop this possibility has come from the collaboration between physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their theory of orchestrated objective reduction proposes that consciousness arises from quantum processes in cellular structures called microtubules, which form part of the cytoskeleton in neurons throughout the brain. According to this theory, quantum information processing in microtubules creates the unified conscious experiences that characterize human awareness. The theory attempts to solve both the hard problem of consciousness and the measurement problem in quantum mechanics by identifying consciousness with the physical process of quantum state reduction. When quantum superpositions in microtubules reach a critical threshold, they collapse according to fundamental features of space-time geometry, creating discrete moments of conscious experience. The Penrose-Hameroff theory has been criticized on both biological and physical grounds. Many neuroscientists argue that microtubules are too far removed from the synaptic processes that most theories of consciousness focus on. Physicists have questioned whether quantum coherence can survive in the warm, noisy environment of living cells for the extended periods that the theory requires. The exotic physics of quantum gravity that the theory invokes remains largely untested and speculative. Yet recent research has provided some support for quantum effects in microtubules, even if not necessarily in the specific way that Penrose and Hameroff originally envisioned. Studies have found evidence for quantum coherence in the protein structures that make up microtubules, and some research has suggested that anesthetics might indeed disrupt quantum processes in these cellular components. More broadly, the field of quantum biology has demonstrated that quantum effects can persist in biological systems under specific conditions, making the possibility of quantum consciousness seem less outlandish than it did when the Penrose-Hameroff theory was first proposed. But even if consciousness does involve quantum processes, this would not automatically resolve the measurement problem. we would still need to understand how conscious observation differs from other types of physical interaction. This is where the question becomes not just scientific, but also profoundly philosophical. If consciousness involves quantum processes, and if these processes can influence other quantum systems, then conscious observers are not simply external agents who passively record information about quantum systems. They are active participants in quantum processes themselves, existing simultaneously in both the quantum and classical realms. Such hybrid systems challenge the mathematical framework of quantum mechanics, which was developed under the assumption that there is a clear distinction between quantum systems and classical measuring apparatus. If conscious observers are themselves quantum systems, then the measurement process becomes a quantum interaction between two quantum systems, rather than an interaction between a quantum system and a classical device. The mathematical description of such interactions requires new theoretical frameworks that can handle the complex interplay between quantum and classical processes in biological systems. Some researchers have begun developing these frameworks, drawing on advances in quantum information theory and open quantum systems to model how quantum effects might persist and influence biological function in partially decohered environments. These developments suggest that the relationship between consciousness and quantum mechanics might be more subtle than either purely materialist or purely idealist approaches typically assume. Rather than consciousness either causing wave function collapse or being irrelevant to quantum processes, consciousness might represent a particular type of quantum information processing that emerges in biological systems capable of maintaining coherence under specific conditions. But this still leaves fundamental questions about the nature of subjective experience and its relationship to physical processes. Even if consciousness involves quantum effects, we still need to explain why these effects should be accompanied by the felt quality of subjective experience rather than simply more complex forms of information processing. The hard problem of consciousness persists regardless of whether consciousness involves classical or quantum physical processes. The persistence of this explanatory gap reflects something deeper about the relationship between objective physical descriptions and subjective conscious experience. Quantum mechanics, like all physical theories, provides a mathematical description of observable phenomena, but it cannot capture the first-person perspective from which those observations are made. The subjective experience of observing a quantum measurement result is not itself described by the quantum mechanical formalism, even though it seems necessary for interpreting what the formalism means. This creates a fundamental asymmetry in our scientific understanding. We can describe quantum systems and their interactions with extraordinary mathematical precision, but we cannot similarly describe the conscious experiences through which we gain knowledge of these systems. Consciousness appears in quantum mechanics not because it explains quantum processes, but because it represents the irreducible, subjective perspective from which those processes are observed and interpreted. The recognition of this asymmetry has led some physicists and philosophers to explore more radical possibilities about the nature of reality and consciousness. Rather than treating consciousness as something that emerges from complex arrangements of matter, some approaches treat consciousness as a fundamental feature of reality that exists alongside matter and energy as a basic constituent of the physical world. These approaches, sometimes called panpsychist theories, suggest that consciousness is not unique to biological systems, but exists in some form throughout the natural world. According to such theories, human consciousness represents a particularly complex and unified form of something that exists more broadly in nature. The apparent connection between consciousness and quantum mechanics might reflect this fundamental status of consciousness as a basic feature of physical reality. But panpsychist approaches create their own conceptual puzzles about how simple forms of consciousness might combine into more complex unified experiences, and about how consciousness relates to the mathematical structures that physics uses to describe the natural world. The combination problem and the problem of psychophysical laws remain as challenging for panpsychist theories as the hard problem of consciousness is for materialist approaches. This is where intuition usually begins to strain. Every attempt to understand the relationship between consciousness and quantum mechanics seems to lead to deeper puzzles rather than clear resolutions. The measurement problem in quantum mechanics and the hard problem of consciousness share a similar logical structure, both involving gaps between objective physical processes and subjective experiences or outcomes that resist reduction to purely physical terms. Some physicists have begun to explore whether these problems might have a common solution in new theoretical frameworks that can accommodate both the mathematical precision of quantum mechanics and the irreducible reality of conscious experience. These approaches often involve fundamental modifications to our understanding of the nature of information, observation, and physical law. Quantum information theory has provided new tools for thinking about these questions by treating information as a fundamental physical quantity rather than just a useful abstraction. In this framework, both consciousness and quantum mechanics involve the processing and transformation of information, but consciousness involves types of information, integration, and interpretation that go beyond what current physical theories can fully describe. The development of quantum computing has added practical urgency to these theoretical questions. Quantum computers must eventually produce classical outputs that can be interpreted by classical computers and human operators, requiring the same kind of quantum to classical transition that puzzles physicists in the context of quantum measurement. Understanding this transition might require new insights into the relationship between quantum information processing and the classical information processing that characterizes conscious cognition. But even these sophisticated informational approaches leave fundamental questions about the nature of consciousness and its relationship to physical processes unresolved. The mathematical framework of quantum information theory provides powerful tools for describing information processing systems, but it cannot capture the subjective quality of conscious experience that seems necessary for understanding what information means. This limitation reflects something deeper about the nature of scientific knowledge itself. Science has been extraordinarily successful in developing mathematical descriptions of objective physical processes, but it has struggled to incorporate the subjective dimension of reality from which scientific observations are made. The persistent appearance of consciousness in discussions of quantum mechanics might reflect this fundamental limitation in purely objective approaches to understanding reality. The recognition of such limitations need not lead to anti-scientific conclusions or mystical thinking. Instead, it might point toward new forms of scientific understanding that can accommodate both the precision of mathematical physics and the irreducible reality of conscious experience. Such understanding would require conceptual frameworks that can bridge the gap between third-person scientific description and first-person conscious experience. Recent developments in the philosophy of mind and cognitive science have begun to explore such frameworks, often drawing on insights from both quantum mechanics and neuroscience. These approaches treat consciousness not as something that can be reduced to purely physical processes, but as a fundamental aspect of how information processing systems relate to the world around them. The inactive approach to cognition, for example, treats consciousness as emerging from the dynamic interaction between organisms and their environments rather than from internal computational processes. According to this view, consciousness is not something that happens inside the brain, but something that emerges from the ongoing coupling between neural activity and environmental engagement. This perspective suggests that consciousness might play a fundamental role in how organisms extract information from quantum systems without necessarily causing wave function collapse through some mysterious psychokinetic mechanism. Instead, consciousness might represent a particular type of information theoretic relationship between biological systems and their environments that allows for the extraction of classical information from quantum processes. Such approaches remain highly speculative, but they illustrate how the question of consciousness in quantum mechanics continues to evolve in unexpected directions. Rather than seeking a final answer to whether consciousness explains quantum mechanics or quantum mechanics explains consciousness, these approaches explore how both consciousness and quantum processes might be aspects of more fundamental informational or relational structures. The experimental investigation of these possibilities requires increasingly sophisticated techniques for detecting quantum effects in biological systems and for correlating these effects with conscious experiences. Recent advances in quantum sensing and neuroimaging are beginning to make such experiments possible, though the technical challenges remain formidable. The detection of quantum coherence in neural processes requires isolating extremely subtle quantum effects from the much larger classical signals generated by neural activity. Similarly, correlating quantum effects with conscious experiences requires careful control of psychological variables that might influence both the quantum measurements and the subjective reports of conscious states. Despite these challenges, some experiments have begun to probe possible connections between quantum processes and consciousness. Studies of anesthetic action have found correlations between the disruption of quantum effects in cellular structures and the elimination of conscious awareness. Other research has investigated whether meditation or other altered states of consciousness involve changes in quantum coherence in neural systems. And so we return to that simple moment where this all began. A physicist in a laboratory, pressing a button, recording a number, announcing a result. From the outside, the most elementary possible interaction between a conscious observer and a quantum system. Yet beneath this apparent simplicity lies something that resists all our attempts at clean explanation. The experiments continue. The mathematics grows more sophisticated. Quantum technologies emerge from research laboratories into practical applications. Yet the conceptual gap that troubled von Neumann in 1932 remains as puzzling as ever. Every interpretation designed to eliminate consciousness from quantum mechanics encounters the same stubborn obstacle. Something must bridge the transition from quantum possibilities to classical actualities, and that something cannot be fully captured by the mathematical formalism of quantum theory itself. Perhaps this persistence reveals something profound about the nature of scientific knowledge. We have built a theory of extraordinary mathematical precision and predictive power, yet it describes reality in terms that seem to require conscious interpretation to become meaningful. The wave functions and probability amplitudes that form the heart of quantum mechanics are not directly observable quantities, but mathematical abstractions that encode information about what can be measured under different experimental conditions. This is not a failure of quantum mechanics, but perhaps a glimpse into the fundamental structure of how conscious beings relate to physical reality. The question is not whether consciousness explains quantum mechanics, or whether quantum mechanics explains consciousness. The question is why these two domains of inquiry seem to intersect in ways that resist clean separation. The experimental investigation of these connections continues to evolve, pushing the boundaries of what current technology can reliably measure while grappling with the profound conceptual challenges of studying consciousness scientifically. Each new result seems to deepen the mystery rather than resolve it, revealing previously unrecognized layers of complexity in both quantum mechanics and conscious experience. And perhaps that is the most illuminating insight of all. The appearance of consciousness in quantum mechanics may not be pointing toward a solution, but toward the limits of purely objective approaches to understanding reality. Both consciousness and quantum measurement involve aspects of the relationship between knower and known that cannot be fully captured from a detached third-person perspective. The silence in that laboratory after the measurement is complete and the result recorded carries within it all the unresolved questions about observation, interpretation, and the nature of physical reality. The physicist knows what happened, but cannot fully explain why it happened the way it did. The conscious observer has gained definite information about a quantum system, yet the mechanism by which quantum possibilities became classical actualities remains as mysterious as it was nearly a century ago. This is not a problem waiting for a solution, but perhaps a fundamental feature of how reality reveals itself to conscious observers. The question refuses to disappear, not because we lack sufficient data or mathematical sophistication, but because it points towards something irreducible in the relationship between mind and world. And in that irreducibility, consciousness keeps appearing in quantum physics not as an answer, but as a reminder of how much about the nature of reality remains genuinely unknown.